Welcome to Math Build. In the sequence of videos we are going to have from now on, we are going to cover topics relating to pure mathematical fields, of which the basics will be very important, and we'll try to make sure we'll do justice to that. And we'll start right away from discrete mathematics. Discrete mathematics. We'll try to see if it is possible for us to cover the whole mathematics from the beginning to the end. And of course, to cover the whole mathematics, we need to start from the main fundamentals. So, welcome to Math Build again. And the first of the videos which we are going to be releasing from now is MTB 001, Math Build 001. And MTB 001 starts with the topic on the fundamentals, basically fundamentals of set theories. So we have fundamentals. These fundamentals will be dwelling mostly on what? Of sets. There's a reason behind it. To have a very good understanding of abstract mathematical concepts, a good knowledge of set theory is required. Understanding of set operations, of sets in general, is very important to achieve that. So we'll kick off with 1.1, which is sets and subsets. Sets in general and subsets. So it's good to start with the definition of a set. So we'll take the definition. My bad. A set is any well-defined collection of objects called the elements or members of the set. Okay? For example, the collection of all wooden chairs, the collection of all one-legged black birds, or the collection of real numbers between 0 and 1. These are all sets. By the term well-defined, we just mean that it's possible to decide if a given object belongs to a collection or not. Almost all mathematical objects are first of all sets, regardless of any additional properties they may possess. The set theory is, in a sense, the foundation on which virtually all of mathematics is constructed. In spite of this, set theory is quite easy to learn, I believe so, and use. So that is it. Set is any well-defined collection of objects called the elements, or members of the set. Okay. So that's where we define it. Examples of we said let's say a collection of all wooden chairs. Okay, collection of all wooden chairs is a set. And by the term well defined, what do we mean? By the term well defined, we mean that it is possible to decide if a given object belongs to a set. Now, one way of describing a set that has a finite number of elements is by listing the elements of the set between braces. Thus, the set of all positive integers that are less than 4 can be written as we have 1, 2, 3. The set of all positive integers that are less than 4. You see, this is a set, a collection of integers. Now, the order in which the elements of a set are listed is not important. So even if 3 comes before 2 or anyhow the order comes up, it is not important. Okay, all possible arrangements of this same set still remain the set. Okay, still equivalent to the set. They are all the same no matter the arrangement. Repetition is not also allowed. If a particular element repeats more than 5 times, so the set still remains the same. So there is no repetition allowed because all the members of the set will still be 1, 2, 3 no matter the repetition. So what I'm trying to mean is the set 1, 2, 3, 1 is still equivalent to this set. Okay, no difference at all. Now, traditionally, uppercase letters, or should I say capital letters, are used to denote sets. So we use capital letters like we have A, B, C, and so on to denote sets, and small letters are used to denote the members of the set. Often, the variables used for the members is X, or A, or B, or C. Y also comes up at times. So these are possible small letters that are used to denote the members of a certain set. Good. Now, there is a way we use to indicate that mathematically that a set has members, or should I say a certain member belongs to a set A. Like for instance, 1 is clearly, if we call this set here, we call this set P. Okay, 1 is a member of P, 2 is also a member of P, and 3 is also a member of P. Now this symbol here stands for an element of, okay, or a member of. So 1, member of P, 2 is a member of set P, 3 is a member of set P. Now what if we say 4 is a member of P? Clearly this is not true. This is not true because 4 is not in the set P. So the best way to say that 4 is a member of P false is 4 is not in P. So we cancel the symbol, like, well, this is how we present it. Sometimes it is inconvenient to denote a set by listing its members, all of its members. Another useful way to define a set is by specifying a property that the elements of the set have in common. We often use the notation P of X to denote the certain property that a particular set, that the elements of a particular set have in common. And at the end, we end up with a P of X. So this is often the way we denote a set with some members by describing the property that the members have in common. And this is read as the set of all X such that P of X holds, okay? Such that P of X holds. Or the set of all X such that P of X. For example, let's say the set of all X such that X is a positive integer, okay? It's a positive integer less than 4, and that boils down to the set what? P, because the set of all X so that X is positive integer less than 4 means we are going to have a set of only integers starting from 1, 2, 3, and 4. Good. Which is P. The set of the set consisting of all the letters of the word byte. So that's the first example we want to look at. The set consisting of all the letters in the word byte. Now the set of all letters in the word byte can be denoted as set of small letter b, y, t, e. So this is the set that consists of all the letters in the word byte, by listing all the members by it. Now the other way we can still write the same set is by saying that the set of all x, such that x is a letter, in the word byte. So these are the two main major ways of denoting sets, of expressing sets. We have by listing all its member, or by using a statement that applies to the members. Second example we can look into is let's see. we have a set of positive integers. A set of positive integers as a set of all x can be written as a set of all x such that x is a positive integer. It's a positive integer. Now this set consists of all counting numbers from 1, 2, 3 till infinity. Okay, so if you are to list all the members, this is what we'll get. Okay. Now watch, since the square root of a real number is always non-negative. What does that literally mean? It means it's positive. Since the square root of a real number is always non-negative, that means no, my bad. It's a very wrong statement. Since the square of a real number is always non-negative, that is something like x squared, it has to be greater than or equals to 0. So it's always non-negative. Now let's suppose we have the situation where x squared is actually equals to a negative value minus 1. Technically, x ceases to be, x is no longer real. That's what it means. If x squared is equals to negative 1, that means x is no longer real, because it is a fact that the square of real numbers is always positive. Now, so we can write something. We can write a set of all x such that x is a real number. It's a real number, and x squared is equals to minus 1. What do you think? First, we first of all stated before that if the square of x is a negative value, that means x is no longer real, and we are trying to define a certain set of all possible x such that x is first of all a real number and its square is minus 1. Of course, this is impossible, so that means there is no such element in the set of real numbers. So it's an empty set, and this is how we denote an empty set, or we use this. Okay, these are the two ways of denoting an empty set. Good. Now we are going to talk about subsets. Let's talk about subsets. Now, if every element of a certain set, let's say capital letter A, is also an element of another set, let's say capital letter B, that is, if whenever a certain member of A is also a member of B, we say that that set A is a subset of B, okay, or that the set A is contained in B. There's a mathematical way of writing this. So let's just say we have like, okay, this is a case I'm talking of. We have two sets. Let's say the sets A and B. Let's say this is A and this is B, and this is the element of A. Let's call it X. We see that clearly X is in A, and also X is in B because A is contained in B. So as a result, X is in A and is also in B because the set B itself is found within, no, the set A itself is found within B. Okay, so we are trying to say if every element of A is also an element, of B. That is, if whenever X is in A, then that same X is in B. We say that A is a subset. It's a subset of B. Say that A is a subset of B, or that A is contained in B. So the two cases, they're the same actually. A is a subset of B, or A is contained in B. And we denote this mathematically as A subset of B. Good. What if A is not a subset of B? How do we do that? Like, let's say we have A here, and then we have B here. You see clearly that though there are some elements of A that are in B, or B that are in A, X in A here is not in B. Okay, so clearly we can't say that A is a subset of B here. So if A is not a subset of B, how do we write it? We write it in this we write it in this form: A is not a subset of B, just as we see here. So this depicts what A is not a subset of B. Meanwhile, this shows that A is a subset of what? B. That is it. Okay. Now, for any set A, since there are no elements of how do I explain it? Of the empty sets that are not in A, we have that the empty set is a subset of A. Let me repeat again. For any set A, since there are no elements of the empty set that are not in A, we say that the empty set is a subset of A. As we're saying that every empty set is a subset of a set, because there are no elements in the empty set that are not in A. Now, it is easy to see that two sets are equal, that is, A is equals to B, if and only if A is contained in B, and what? B is contained in what? A. This is the condition for us to say two sets are equal. Okay, A is equals to B, provided these two conditions hold, that A is in B and B is in A. This simple statement is the basics for the proofs of many statements about sets that have to do with one is equals to the other. Thank you for staying with us for so far. Thank you for watching. Thank you for being patient. And we also thank you if you can subscribe and hit the like button. We'll be grateful. We say thank you again. Thank you. Thank you. See you in the next class.